Block 1, the Pacific Sky, and the need for a new champion. The 8th of December, 1941. A profound stillness hung over the vast expanse of the Pacific Ocean, a quietude that was about to be shattered for generations to come. In the wake of events that would forever alter the course of history, the skies above this immense theater of operations became a chessboard of unparalleled consequence. Here, among the scattered Emerald Islands and the endless blue, the narrative of air superiority was being written, and for a time, it was written with a swift and elegant hand by the pilots of the Japanese Imperial Navy. Their primary instrument was a machine that seemed to have been crafted from the very air it commanded. The Mitsubishi A6M, known to its adversaries as the Zero. This aircraft was a marvel of engineering, a testament to a design philosophy that prioritized agility above all else. It was light, incredibly maneuverable, and in the hands of a skilled pilot, it could dance through the clouds, turning inside its opponents with a grace that was both beautiful and terrifying. For the American pilots flying the rugged but comparatively sluggish Grumman F-4F Wildcat, an encounter with a Zero was a lesson in humility and a desperate struggle for survival. The Wildcat was tough, a flying anvil that could absorb tremendous punishment and bring its pilot home, but it could not turn with the Zero. It could not climb with the Zero. In the intricate, swirling dogfights that characterized the early air battles over places like Wake Island and the Coral Sea, the Zero was the undisputed master of the close-range turning fight. American strategy had to adapt, evolving into tactics like the Thatch Weave, a brilliant cooperative maneuver where two Wildcats could cover each other's tails, turning their defensive posture into an offensive trap. Yet, this was a reactive measure, a solution born of necessity against a superior foe. What was truly needed, what the engineers and designers back in the United States were working tirelessly to create, was not just a counter, but a revolution. They needed a new champion. The call for this new aircraft had gone out years earlier, long before the world was plunged into its global conflict. The United States Navy, looking ahead to the future of carrier-based aviation, had issued a demanding set of requirements in 1938. They envisioned a fighter that would not only replace the aging biplanes of the era, but would also represent a quantum leap in performance. It needed to be fast, heavily armed, and possess a range that would allow it to strike deep into enemy territory, protecting the fleet and projecting its power across the seas. The challenge was immense. Building a high-performance aircraft is a delicate balance of trade-offs: power, weight, aerodynamics, and armament. Pushing the envelope in one area often means compromising in another. To make an aircraft faster, you might need a larger engine which adds weight, which in turn requires larger wings, increasing drag, and negating some of the speed gained from the more powerful engine. It is a complex, circular puzzle. Several companies submitted proposals, but it was the design from Vought Aircraft Company, led by the visionary chief designer Rex Beisel, that truly captured the imagination and promised to shatter the existing paradigms. Their proposal, designated the V166B, was audacious. It was built around the most powerful aircraft engine then in development, an 18-cylinder, air-cooled radial behemoth that promised to deliver an unprecedented 2,000 horsepower. This engine was the heart of the concept, the central pillar around which everything else would be built. The designers at Vought understood that to defeat the nimble fighters of the future, they could not simply try to outturn them. Instead, they would pursue a different philosophy: overwhelming power and speed. Their creation would not dance with its opponents. It would dictate the terms of the engagement from a position of superior energy and altitude. It would strike like a thunderbolt from above and climb away with such astonishing speed that retaliation would be impossible. The aircraft they designed was a monster, a machine of immense size and presence. To harness the colossal power of its engine, it required a propeller of enormous diameter, over 13 feet across. This presented a significant engineering problem, particularly for a carrier aircraft. A propeller that large would strike the deck during landing, unless the landing gear was made exceptionally long and spindly, which would make it too weak to withstand the violent controlled crashes that constitute a carrier landing. The solution that Beisel and his team devised was not just clever, it was iconic. They inverted the wing root, creating a distinctive, bent, or gull wing shape. This design allowed the wing to meet the fuselage at a higher point, providing the necessary ground clearance for the massive propeller while keeping the landing gear short, stout, and incredibly strong. This unique silhouette, born from a practical engineering solution, would give the aircraft its famous profile and contribute to its legendary status. The initial prototype, the XF-4U-1, first took to the sky on the 29th of May, 1940. On its test flights, it quickly began to demonstrate its incredible potential. In October of that same year, it became the first American single-engine fighter to exceed 400 miles per hour in level flight. The promise was there, a tantalizing glimpse of a future where American pilots would hold the advantage. But the path from a promising prototype to a combat-ready warplane is long and fraught with challenges. The design had teething problems. The massive engine and its torque made takeoff and landing tricky. Visibility from the long-nosed cockpit was poor, a critical flaw for carrier operations. The development was a grueling process of refinement, of solving one problem only to uncover another. As the engineers in Connecticut worked, the world changed. The war in Europe raged, and the storm clouds gathered over the Pacific. The need for this new fighter became more than a strategic goal. It became a desperate, urgent necessity. The pilots flying the Wildcats and Airacobras in the Pacific were holding the line with courage and skill. But they were paying a heavy price. They needed a machine that could meet the zero on its own terms, and then surpass it. An aircraft that could climb higher, fly faster, and strike harder. The hopes of a nation and the fate of thousands of young aviators rested on the shoulders of the engineers and the promise of their new creation, the F-4U Corsair. It was a machine conceived in peace, forged in the crucible of war, and destined to become a legend in the unforgiving skies of the Pacific. Block 2, the heart of a giant, the R-2800 Double Wasp. At the very core of the Corsair's revolutionary design, nestled behind its massive propeller and shrouded by its distinctive cowling, lay the source of its immense power and the key to its future dominance. This was not merely an engine. It was a masterpiece of mechanical engineering, a symphony of forged steel, aluminum, and controlled combustion. It was the Pratt & Whitney R-2800 Double Wasp. To comprehend the Corsair, one must first comprehend its heart. The Double Wasp was a two-row, 18-cylinder, air-cooled radial engine. The designation R-2800 referred to its displacement, 2,804 cubic inches, or roughly 46 liters. This was an engine of staggering proportions, larger than the engines found in many tanks of the era. Yet, it was designed to be bolted to the front of a fighter aircraft and operate with the precision of a fine watch under the most extreme conditions imaginable. Its development had begun in 1937, a time when 1,000 horsepower was considered the benchmark for a high-performance fighter engine. The team at Pratt & Whitney aimed to double that figure, a goal so ambitious that many in the aviation community considered it borderline fantasy. Creating such an engine was not simply a matter of making the cylinders bigger or adding more of them. It was a challenge that pushed the very limits of metallurgy, thermodynamics, and manufacturing technology. Each of the 18 cylinders was a self-contained power plant, with its own piston, valves, and spark plugs. The engine operated on a 4-stroke cycle, and with 18 cylinders firing in a meticulously timed sequence, the result was a continuous, overlapping series of power pulses that translated into a smooth torrent of raw, unadulterated power. A single rotation of the crankshaft involved 9 separate combustion events, creating a deep, resonant roar that would become the Corsair's auditory signature, a sound that would strike fear into its opponents and reassurance into the hearts of the ground troops it supported. The sheer power output of 2,000 horsepower at takeoff was only part of the story. An aircraft engine's performance at sea level is one thing. Maintaining that power at high altitudes, where the air is thin and offers less oxygen for combustion, is another challenge entirely. This is where the Double Wasp's true genius lay, particularly in its sophisticated supercharging system. A supercharger is essentially an air compressor, driven by the engine itself, that forces a denser mixture of air and fuel into the cylinders than would be drawn in by normal atmospheric pressure. This allows the engine to breathe at high altitude, as if it were still at sea level, maintaining its power output far into the thin, cold air of the upper atmosphere. The R2800 was equipped with a 2-speed, 2-stage centrifugal supercharger. This was a complex and brilliant piece of machinery. The 2-stage part meant it had 2 impellers, or spinning fans, that compressed the air sequentially, increasing its density far more effectively than a single-stage unit. The 2-speed feature allowed the pilot to select a lower gear for the supercharger at low to medium altitudes and a higher gear for high-altitude flight, optimizing the engine's performance across its entire operational envelope. This system was the key to the Corsair's ability to outperform its rivals, where it mattered most, in the vertical plane. While a Mitsubishi Zero's engine performance began to fade significantly above 15,000 feet, the Double Wasp, with its supercharger engaged in high gear, was just hitting its stride. This gave Corsair pilots a decisive tactical advantage. They could climb above their opponents, storing potential energy in the form of altitude, and then choose the time and place of the engagement, converting that altitude into blistering speed in a dive. This technological superiority was the result of a massive industrial and scientific effort. The metals used in the Double Wasp's construction had to be of the highest quality, capable of withstanding incredible temperatures and pressures. The pistons, forged from aluminum alloy, traveled up and down in their steel cylinder barrels, thousands of times per minute. The crankshaft, a complex, multi-jointed piece of machined steel, had to transmit the combined force of all 18 cylinders to the propeller without failing. The tolerances were measured in 10,000ths of an inch. The assembly of each engine was a painstaking process, carried out in vast, clean factories by a skilled workforce that included thousands of women who had entered the industrial labor force for the first time. Each of the nearly 364,000 Double Wasp engines built was a testament to this incredible mobilization of human and industrial resources. This engine was not only powerful, but also remarkably rugged. The air-cooled design, while creating a larger frontal area than liquid-cooled inline engines, made it resilient to combat damage. A single, stray round might puncture a radiator on a liquid-cooled engine, causing it to lose coolant and seize within minutes. A radial engine like the Double Wasp, however, could often sustain significant damage to one or more cylinders and continue to operate, providing enough power for a pilot to disengage and limp back to base. This robustness, combined with the Corsair's heavy armor and self-sealing fuel tanks, created an aircraft that was not only a potent offensive weapon, but also a remarkably survivable one. And so, the solution to the problem of accommodating the giant Hamilton Standard propeller was born from the necessities dictated by this engine. The inverted gullwing was a direct consequence of the decision to use the R2800. It was a visual representation of the Corsair's entire design philosophy. That power was paramount. The aircraft's very shape was sculpted by the demands of its mighty heart. The engineers at Vout had made a monumental bet, staking the success of their design on a new and unproven engine. It was a bet that would pay off spectacularly, creating an aircraft that was, for a time, the most powerful fighter in the world. The Double Wasp was more than a collection of metal parts. It was the soul of the Corsair, the source of its legendary speed, its astonishing climb, and the thunderous, whistling sound that would earn it the nickname Whistling Death. Block 3. Whispers from the East, the Japanese perspective. Thousands of miles across the Pacific, in the design offices of companies like Nakajima and Mitsubishi, a different philosophy of aircraft engineering held sway. It was a philosophy born of different strategic needs, different industrial capabilities, and a different cultural approach to the art of warfare. The Japanese aviation industry, personified by brilliant designers like Jiro Horikoshi, the father of the Zero, had achieved extraordinary things. They had created aircraft that were, in the early years of the war, the envy of the world. The guiding principles behind these designs were lightness, simplicity, and above all, unparalleled maneuverability. The Mitsubishi A6M0 was the ultimate expression of this creed. It was a work of art, stripped of every ounce of unnecessary weight. It had no armor plating to protect the pilot, no self-sealing fuel tanks to prevent fires. Its very structure was a delicate lattice of lightweight alloys. This obsessive focus on weight reduction gave the Zero its phenomenal performance at low to medium altitudes. It could outturn any opponent, climbing and rolling with a responsiveness that felt less like a machine and more like a living extension of the pilot's will. For the pilots of the Imperial Japanese Navy, who were trained to a razor's edge in the art of the dogfight, the Zero was the perfect instrument. They were masters of the swirling, close-quarters aerial duel, and the Zero was the finest dueling weapon of its time. This design philosophy was not born in a vacuum. Japan was a nation with limited industrial resources compared to the United States. They could not afford to build massive, complex engines in the same quantities, nor could they refine the high-octane fuels needed to power them as readily. Their engineering brilliance lay in achieving maximum performance from limited means. They focused on clean aerodynamics and radical weight saving to compensate for their less powerful engines. The Nakajima Ki-43, the Oscar used by the Imperial Army, followed a similar path. It was even lighter and more agile than the Zero, a pure dogfighter that relied on its nimbleness for both offense and defense. However, the architects of Japan's air power were not blind to the limitations of their approach. They were astute and highly intelligent engineers, men like Kenji Tanaka and Hiroshi Akiyama, composite figures representing the talented teams at the heart of the industry. They understood that the Zero's strengths were also its greatest weaknesses. The lack of armor and self-sealing tanks made it incredibly vulnerable. A few well-placed shots from the heavy machine guns of an American fighter could cause a Zero to disintegrate or burst into flames. Furthermore, while its performance was superb at lower altitudes, its engine, equipped with a less efficient supercharger than its American counterparts, struggled in the thin air above 20,000 feet. The pilots themselves knew this. They were proud of their Zeros, but they also spoke of the lighter-like tendency of their aircraft to catch fire. They were keenly aware that their survival often depended on not getting hit in the first place. By mid-1942, whispers began to arrive from the front lines in the Solomon Islands and New Guinea. They were fragmented reports, battlefield rumors from pilots who had survived encounters with a new and unsettling American fighter. The descriptions were often contradictory, colored by the stress and confusion of combat. Some pilots described an aircraft with a strange, bent wing. Others spoke of its incredible speed, especially in a dive. But one detail was consistent across almost all the reports: the sound. It was a deep, resonant roar, unlike the higher-pitched whine of other Allied fighters. And when it dove, the wind rushing through its engine cowlings and wing-mounted oil coolers created a high-pitched shriek, a terrifying banshee wail that preceded its arrival. The name, Whistling Death, began to circulate in hushed tones at airbases across the South Pacific. Initially, the engineers and intelligence officers back in Japan were skeptical. They had a healthy respect for American industrial power, but they also believed in the superiority of their own design philosophy and the unmatched skill of their pilots. They analyzed the reports, trying to piece together a coherent picture. Was this new aircraft the P-38 Lightning with its twin booms? Or perhaps the new Grumman F-6F Hellcat, which they knew was in development as a successor to the Wildcat? The descriptions didn't quite fit. The bent wing was a unique identifier. They cross-referenced it with intelligence reports and eventually identified the likely candidate: the Vought F-4U Corsair. The specifications they could glean from open sources and intelligence were alarming. The claimed horsepower of its engine, 2,000, seemed almost unbelievable. Japanese engines of the time, like the Nakajima Sakai in the Zero, produced just over 1,000 horsepower. Their newest and most advanced engine, the Homare, was designed to reach the 2,000 horsepower class, but it was plagued with reliability problems and was not yet ready for mass production. The idea that the Americans had already fielded such a power plant in large numbers was a deeply troubling thought for men like Tanaka and Akiyama. It suggested a gap not just in a single aircraft's performance, but in fundamental engine technology. They discussed it in their quiet, methodical way in the meeting rooms of Nagoya and Ota. If the reports were true, this Corsair represented a direct challenge to their entire doctrine of air combat. An aircraft with such a massive advantage in speed and climb rate could refuse to engage in a turning fight, the very arena where their pilots excelled. It could use boom and zoom tactics, diving from an untouchable altitude, making a single, devastating firing pass, and then using its superior power to climb back to safety, leaving the Zero pilots helpless to follow. This new American philosophy was one of brute force, of energy fighting over maneuverability. It was a style of combat dictated by the laws of physics, and the Corsair's engine gave it a much larger reservoir of physical energy to draw upon. The engineers longed for concrete data. A pilot's report, however vivid, was subjective. They needed to see the machine for themselves. They needed to touch its metal skin, to measure its wings, and most importantly, to look inside its cowling and study the engine that was causing such concern. An opportunity to capture one of these new aircraft, even a wrecked one, would be an intelligence prize of the highest order. It would allow them to confirm their fears or dismiss them, to understand the technology they were up against, and to begin formulating a response. Until then, all they had were the whispers from the front, the growing legend of a bent-winged monster with a voice like a banshee and a heart of thunder. Block 4, First Encounters and the Brutal Calculus of Energy. August 1942. The skies over the Solomon Islands became the crucible where the old and new philosophies of air combat would be tested by fire. It was here, above the lush green jungles of Guadalcanal and the sparkling waters of the Slot, that the F-4U Corsair, initially flown by United States Marine Corps squadrons, made its combat debut. For a young Marine pilot, climbing into the cockpit of a Corsair for the first time was an awe-inspiring experience. The cockpit was perched high off the ground, and the view forward was dominated by the immense length of the nose, housing the massive double Wasp engine. The takeoff run was a controlled explosion, the torque from the engine trying to twist the aircraft off the runway, requiring a firm hand and a strong leg on the rudder. But once airborne, the pilot could feel the raw power coursing through the airframe. It was not the delicate, nimble feeling of a Zero. It was the sensation of being strapped to a thoroughbred racehorse, a creature of immense strength and speed, eager to run. The American pilots had been rigorously trained to fight to the Corsair's strengths and avoid its weaknesses. The instructors had drilled one simple lesson into their heads until it became instinct. Never, ever try to turn with a Zero. To do so was to play the enemy's game, a game the Corsair was not designed to win. Instead, their strategy was based on the brutal, simple calculus of energy. Altitude is potential energy. Speed is kinetic energy. The Corsair, with its powerful supercharged engine, could generate and store more energy than any Japanese aircraft. The new combat doctrine was built around this single, overwhelming advantage. It was called boom and zoom. A flight of Corsairs would arrive over the combat zone at a high altitude, often above 25,000 feet, positioning themselves between the sun and their expected targets. From this lofty perch, they would scan the skies below for the telltale glint of enemy aircraft. When a formation of Zeros was spotted, the flight leader would pick a target and roll his Corsair into a dive. In that dive, the Corsair transformed. The potential energy of its altitude was converted into breathtaking kinetic energy. The aircraft accelerated rapidly, the airframe groaning under the strain, the wind screaming its now famous whistle. The pilot would be pushed into his seat by the G-forces, his entire focus narrowed to the target growing in his gun sight. For the Japanese pilot below, the experience was terrifying. The first warning was often the sound, a high-pitched shriek that seemed to come from nowhere. Then, a dark shape would materialize from the glare of the sun, growing in size at an alarming rate. The Corsair, diving at well over 400 miles per hour, would be on top of the Zero formation in a matter of seconds. The Japanese pilot had no time to react, no opportunity to use his aircraft's superior agility. The Corsair pilot would line up his target, and for a brief, violent moment, the sky would be filled with the percussive sound of 6 .50-caliber Browning machine guns. These weapons fired heavy slugs at a high rate of fire, and their impact was devastating to the lightly built Zeros. The stream of tracers would lash out, and if the pilot's aim was true, the target would simply cease to be a threat, often trailing a plume of dark smoke as it fell away. The attack was over as quickly as it began. The Corsair pilot would not linger to admire his work or to engage in a turning fight. The moment his pass was complete, he would pull back on the stick, and the true magic of the double Wasp engine would be revealed. Even with the momentum from its dive bled off in the pull-up, the Corsair had so much residual energy and raw power that it could convert its speed back into altitude with astonishing efficiency. It would rocket back up into the vertical, climbing at a rate that the pursuing Zero pilots could only watch with a mixture of frustration and disbelief. Their lighter aircraft, designed for horizontal maneuvering, simply did not have the power to follow. They would hang on their propellers, their engines straining, only to watch the Corsair pull away, growing smaller and smaller until it was just a speck, ready to set up another attack from its high-altitude sanctuary. This new form of combat was impersonal, methodical, and brutally effective. It was a rejection of the romantic notion of the chivalrous dogfight, the one-on-one duel of champions. It was aerial warfare as an industrial process, where superior technology and energy management were used to achieve victory with maximum efficiency and minimum risk. For the Japanese pilots, it was a profound shock. They were brave, highly skilled, and aggressive, but their training and their aircraft had not prepared them for this. They were being hunted from a dimension they could not reach. A surviving Zero pilot returning to his base at Rabaul or Bougainville would have a harrowing story to tell. He would speak of an enemy that appeared as if from nowhere and vanished just as quickly. He would describe the futility of trying to turn and fight, of watching the American fighter climb away as if tethered to a powerful, invisible winch. These encounters began to erode the sense of invincibility that Japanese naval aviators had enjoyed in the early years of the war. They were still masters of the low-altitude turning fight, and if a Corsair pilot made the mistake of getting slow and trying to mix it up with them, he would pay the price. But the American pilots were learning quickly. They flew with discipline, adhered to their energy fighting tactics, and used their technological advantage to its fullest. The legend of the Whistling Death was no longer a rumor. It was a harsh reality being written in smoke and fire across the skies of the South Pacific. And for the engineers back in Japan, the urgent need to understand this new threat, to get their hands on the machine that was changing the very nature of the air war, became a matter of paramount importance. Block 5. A fallen giant on a distant shore. The conflict in the South Pacific was a sprawling, chaotic affair, fought over hundreds of remote, jungle-choked islands, separated by vast stretches of unpredictable ocean. Airfields were often little more than hastily cleared strips of crushed coral, and weather could change in an instant, from clear blue skies to blinding tropical squalls. In this environment, even the most robust aircraft were pushed to their limits. Mechanical failures, navigational errors, and the ever-present threat of enemy action meant that not every aircraft that took off returned to its home base. It was on one such day in mid-1943 that a lone F-4U Corsair found itself in serious trouble. The pilot, a young Marine lieutenant, was returning from a fighter sweep over a Japanese-held island. The mission had been successful, but his aircraft had been struck by anti-aircraft fire. The damage was not critical at first. A few jagged holes in the wing and a noticeable vibration from the engine. But as he flew back towards his base, the vibration grew worse. The deep, steady roar of the double Wasp engine faltered, replaced by a rough, sputtering cough. A thin trail of black smoke began to stream from the cowling. The pilot checked his gauges. Oil pressure was dropping rapidly. He knew he was not going to make it back. His heart pounded in his chest, a mixture of adrenaline and cold disappointment. Below him was a seemingly endless expanse of blue water, dotted with small, jungle-covered islands. His training kicked in. He radioed his position, informed his squadron of his situation, and began to look for a place to put the wounded bird down. He spotted a small island with a strip of sandy beach, a tiny sliver of hope in a desperate situation. Making a forced landing, especially with a dead stick or failing engine, is one of the most difficult things a pilot can do. For a Corsair pilot, it was even more challenging due to the poor forward visibility over the long nose. He would have to make his approach in a continuous turn to keep the landing area in sight. The pilot fought with the controls, the aircraft feeling heavy and unresponsive. He lowered his landing gear and flaps, his mind a whirlwind of checklists and procedures. He had a duty, not just to survive, but to deny the enemy his aircraft. As he descended, he knew he was over enemy-held territory. The Corsair was one of the newest and most valuable assets in the American arsenal. Its secrets, particularly the secrets of its engine, were worth more than any single pilot's life. He knew what he was supposed to do. If the landing was successful, he was to destroy the aircraft, using the onboard incendiary charges, or, if necessary, his own sidearm to puncture the fuel tanks and ignite them. His descent was a tense, controlled fall. The beach rushed up to meet him. He flared the aircraft at the last possible moment, pulling the nose up to bleed off speed. The wheels touched the soft sand, digging in violently. The Corsair lurched, its left wing dipping and catching the ground. The aircraft spun in a great shower of sand and spray, finally coming to a screeching, metallic halt at the edge of the jungle. For a moment, there was only silence, broken by the hiss of the hot engine and the gentle lapping of the waves. The pilot was shaken, but remarkably unhurt, a testament to the Corsair's rugged construction. His first thought was of his duty. He reached for the switches to activate the destruction charges, but his hand stopped. The impact had been severe. The cockpit was twisted, and the electrical systems were dead. He tried to unfasten his harness, but it was jammed. He was trapped. Through the canopy, he could see figures emerging from the jungle tree line. They were Japanese soldiers, their rifles at the ready. A wave of profound despair washed over him. He had failed. He had failed to return to his squadron, and worse, he had delivered a pristine example of America's most advanced fighter directly into the hands of the enemy. There was a moment of internal struggle, a dark temptation to fulfill his duty in the only way left to him. But his training and his character held him back. His duty was to survive, to endure, and to provide as little information as possible. He raised his hands in a gesture of surrender. The Japanese soldiers approached the aircraft cautiously, their expressions a mixture of suspicion and awe. They had never seen a machine like this up close. It was enormous, far larger than their own fighters. Its dark blue paint was scarred and torn, but its presence was immense. The strange bent wings gave it an almost predatory look, like a great bird of prey brought to earth. They carefully extracted the American pilot, his face a mask of weary resignation, and led him away. For them, he was a valuable prisoner. But the true prize was the aircraft itself. Word was sent immediately to Regional Command. A high-priority message flashed across the airwaves to the naval headquarters at Truk, and then all the way back to Tokyo. An American whistling death had been captured. It was damaged, but its most important components, particularly its engine, appeared to be largely intact. This was the intelligence breakthrough the engineers had been dreaming of. A team of top aviation specialists from the Naval Air Technical Arsenal was ordered to be assembled and dispatched immediately. The logistical challenge was immense. The island was remote with no harbor or airfield. The Corsair would have to be carefully dismantled, piece by piece, under the most primitive conditions. Each component would be labeled, crated, and then loaded onto barges to be transported to a larger ship for the long journey back to the Japanese home islands. It would be a slow, painstaking process, but no effort would be spared. A fallen giant lay on a distant shore, and the secrets it held in its metallic heart were about to be revealed. Block 6. The Unveiling, a study in steel and philosophy. The journey of the captured Corsair was an odyssey in itself. It traveled from the remote Pacific island to the bustling naval yards of Yokosuka, a journey of thousands of miles across a contested ocean. When the crates containing its disassembled parts finally arrived at the Japanese Naval Air Technical Arsenal, a palpable sense of anticipation filled the air. This was more than just another piece of enemy equipment. It was a legend, a ghost they had only encountered in the fleeting, terrifying reports from the front. Now, the ghost was here, ready to be dissected. The team assigned to the project was composed of Japan's finest aeronautical engineers, metallurgists, and engine specialists. Among them were men like our composite figures, Kenji Tanaka, a pragmatic structures expert, and Hiroshi Akiyama, an engine designer with a poet's appreciation for mechanical form. They approached the task with a mixture of intense professional curiosity and grim determination. They were patriots, and their nation was in a desperate struggle. Unlocking the Corsair's secrets was not an academic exercise. It was a vital part of their war effort. The reassembly took place in a large, well-guarded hangar. As the pieces were laid out, the sheer scale of the American aircraft was the first thing that struck the Japanese team. They were accustomed to the lithe, almost delicate proportions of the Zero. The Corsair, by contrast, was a brute. Its fuselage was broad and deep. Its landing gear struts were as thick as a man's arm. The wing spars, when laid bare, were massive extrusions of high-strength aluminum alloy. Tanaka, the structure's engineer, ran his hands over the flush, riveted skin. He noted the thickness of the metal, the robust internal bracing. He meticulously measured the armor plate that had been installed around the cockpit and behind the pilot's seat. It was over half an inch of hardened steel. He then examined the fuel tanks, which had been removed from the wings. They were lined with a thick, rubber-like material designed to swell and seal punctures from enemy fire. These two features alone, heavy armor and self-sealing tanks, represented a profound difference in design philosophy. Japanese design, dictated by the need to save weight, had eschewed such protections. The life of the pilot and the integrity of the aircraft were entrusted to the pilot's skill in avoiding being hit. This American machine, however, was built with the assumption that it would be hit. It was designed to absorb punishment, to protect its pilot, and to keep flying. It was a philosophy of survivability, of industrial attrition. It spoke of a nation that could afford the extra weight, the extra complexity, and the expensive materials because it valued the lives of its highly trained pilots and had the industrial capacity to build machines that could protect them. The team studied the manufacturing techniques. The Corsair was a product of mass production on an epic scale. While there was evidence of skilled hand finishing in some areas, the overall impression was one of standardized, interchangeable parts. The wiring harnesses were neatly bundled and labeled. The hydraulic lines were color-coded. Everything was designed for efficient assembly and, just as importantly, for rapid repair in the field. This was another revelation. Japanese aircraft were often masterpieces of craftsmanship, but they could be difficult to maintain under primitive forward-based conditions. The Corsair was designed to be kept in the fight by crews of young mechanics with standardized training and a good set of tools. It was a machine built for a long, grinding war of logistics and supply. The 650 caliber machine guns, 3 in each outer wing panel, were another point of focus. Their ammunition boxes held a staggering number of rounds, giving the Corsair tremendous firepower and endurance in a fight. The mechanisms for feeding the ammunition were simple, reliable, and powerful. But all of these observations, as insightful as they were merely the prelude to the main event. They were the study of the beast's claws, its hide, and its skeleton. The engineers knew that the true secret, the source of its legendary performance, lay hidden beneath the large, streamlined cowling that formed the nose of the aircraft. A team of mechanics, guided by the engineers, carefully began to remove the dozens of fasteners holding the cowling in place. There was a quiet intensity in the hangar. The metallic clicks of the wrenches echoed in the cavernous space. Finally, the last fastener was removed. Several men carefully lifted the large, curved panels of aluminum away. And there it was. Exposed to the light of the hangar, sitting in its mounting cradle, was the Pratt & Whitney R2800 Double Wasp. For a long moment, the engineers simply stood and stared. They had seen diagrams and photographs, but nothing could prepare them for the physical reality of the engine. It was a dense, complex, and utterly overwhelming piece of machinery. 2 rows of 9 cylinders each radiated out from a central crankcase, their cooling fins creating an intricate, beautiful pattern. A complex web of ignition wires, oil lines, and control linkages snaked around the cylinders. At the rear of the engine was the large, formidable housing of the 2-stage supercharger. Hiroshi Akiyama, the engine specialist, felt a shiver of what could only be described as professional awe. It was, to his eyes, a mechanical marvel. It was not elegant in the way a Japanese engine was elegant. It did not have the polished, minimalist perfection of a Nakajima Sakai. It was a statement of industrial might, a declaration of power rendered in metal. It was beautiful in its sheer, uncompromising functionality. He knew, just by looking at it, that this engine was the product of a different world, a world of unlimited resources, advanced metallurgy, and a relentless pursuit of power. The unveiling was complete. Now, the real work would begin, the careful, methodical dissection of the giant's heart. Block 7. The Revelation of Power, a tale of two technologies. With the double WASP engine now fully exposed, Hiroshi Akiyama and his team of specialists began the most critical phase of their analysis. The engine was carefully detached from its mounts and moved to a specialized workshop, a sterile environment where every component could be examined without distraction. This was not merely a process of reverse engineering. It was an act of industrial archaeology, an attempt to understand the thinking, the technology, and the capabilities of the nation that had created it. The first step was a meticulous external examination. Akiyama and his colleagues marveled at the quality of the casting and forging. The crankcase, the central component that held the engine together, was a complex and beautiful piece of forged aluminum, both light and incredibly strong. The cylinders were a composite construction, with steel barrels for durability screwed into cast aluminum heads for efficient heat dissipation. This was a technique they were familiar with, but the precision of the machining and the quality of the alloys were of a standard that was difficult for Japanese industry to consistently replicate. They then turned their attention to the engine's complex systems. The ignition system, with its two independent magnetos each feeding a separate set of 18 spark plugs, was a model of redundancy, designed to keep the engine running even if one system failed. The plumbing for the oil and fuel lines was a masterpiece of organization, a stark contrast to some of the more chaotic arrangements in their own prototypes. But it was the supercharger at the rear of the engine that drew the most intense scrutiny. This, they knew, was one of the key technological differentiators. They carefully disassembled the two-stage, two-speed unit, laying out its components on a clean, white cloth. The two impellers, the fan-like wheels that compressed the air, were machined from high-strength aluminum alloy. Their complex, curved blades were shaped to move air with maximum efficiency and minimal turbulence. The gearing that allowed the pilot to switch between low and high speed was intricate yet robust. Akiyama understood immediately the immense advantage this system provided. It was like giving the engine a different set of lungs for high-altitude flight, allowing it to breathe freely in the thin, cold air where Japanese engines began to starve. As they delved deeper, they made a discovery that was both humbling and astonishing. They took samples from the engine's key components, the pistons, the connecting rods, the crankshaft, and sent them to the metallurgy lab for analysis. The results that came back confirmed their deepest concerns. The American alloys were superior. They contained trace elements like nickel, chromium, and molybdenum in quantities that Japanese industry, strained by wartime shortages, struggled to acquire. These advanced alloys allowed the engine's components to withstand much higher temperatures and internal pressures. This meant the American designers could run the engine harder, extract more power from every combustion cycle, and do so with a higher degree of reliability. It was a stark reminder that a war is fought not just by soldiers and pilots, but by miners, metallurgists, and factory workers. The technological gap was not just in the design. It was in the very material science that underpinned it. Akiyama's team then turned to the internal components. They meticulously disassembled one of the cylinders, examining the piston and the valve assembly. The precision was breathtaking. They compared the design to their own most powerful engine, the Nakajima Homare. The Homare was, on paper, a brilliant design, intended to produce a similar 2,000 horsepower from a similarly sized 18-cylinder configuration. It was a source of national pride. But the Homare was notoriously temperamental. It was difficult to manufacture, it suffered from cooling problems, and it rarely produced its rated power reliably in the field. Looking at the components of the double WASP, Akiyama began to understand why. The American engine was designed for manufacturability and reliability from the ground up. Its components were slightly heavier, slightly less elegant than their Japanese counterparts, but they were more robust. The cooling fins on the cylinders were deeper, providing more surface area to dissipate the immense heat. The internal oil passages were larger, ensuring better lubrication under high stress. The Double Wasp was not a delicate racing engine. It was a workhorse, designed to run at maximum power for hours on end, to be torn down and rebuilt by mechanics, and to endure the rigors of combat. It was a product of a different mindset. While Japanese engineering often pursued the pinnacle of performance, sometimes at the expense of reliability, American engineering seemed to prioritize dependable, repeatable performance. The final piece of the puzzle was the sheer power figure itself, 2,000 horsepower. For the Japanese engineers, this number had been an abstract figure in an intelligence report. Now, having seen the engine's construction, they understood how it was achieved. It was a combination of large displacement, high-quality materials, superior fuel, and, most critically, the incredibly efficient two-stage supercharger. They calculated the pressures and forces inside the cylinders during operation and were staggered by the results. The Double Wasp was a brute, a controlled cataclysm of internal combustion. Akiyama convened a meeting with his team and the senior naval aviation officials. The atmosphere was somber. He laid out their findings calmly and methodically. He explained that the Corsair's engine was not just a scaled-up version of existing technology. It represented a generational leap. It was the product of a massive, integrated industrial ecosystem that could produce high-strength alloys, high-octane fuel, and precision components on a scale that Japan could not hope to match. He concluded his report with a simple, chilling statement. "We cannot build this engine today," he said, the words hanging heavy in the air. "And we cannot build an engine that will reliably perform at this level with the resources we have available." The revelation was complete. The Corsair's power was not a trick or a fluke. It was the result of a fundamental technological and industrial superiority. They now understood, with painful clarity, why the Corsair could climb into the sky and leave their best fighters behind. It was powered by a heart of a different order, a heart forged in a fire that their own industry could not kindle. Block 8. The impossible climb. A verdict in the sky. The analysis on the ground was conclusive, but the military leadership needed more than just engineering reports and metallurgical analyses. They needed to see the Corsair in action, to quantify its performance against their own best aircraft, flown by their own best pilots. The captured Corsair, which had been painstakingly reassembled and repaired using custom-fabricated parts where necessary, was prepared for a series of test flights. The task of flying the alien machine was given to Lieutenant Commander Minoru Genda, a fictional but representative figure embodying the skill and experience of Japan's elite naval test pilots. Genda was a veteran, a man who had mastered the delicate art of flying the Zero and had a deep, intuitive understanding of aerial combat. He approached the Corsair with a mixture of professional respect and deep-seated suspicion. It was the machine that had been outclassing his comrades, and he was determined to understand its strengths and, more importantly, to find its weaknesses. His first flight was a revelation. The pre-flight checklist was complex, the cockpit filled with a bewildering array of gauges and switches. The takeoff was, as he had been warned, a struggle against the immense torque of the engine. But once he was airborne and had retracted the landing gear, he felt the aircraft's true nature. It flew with a sense of immense, unshakable stability. It was not nimble like his Zero. It was a freight train on wings, a platform of immense power and purpose. He spent the first few flights simply getting a feel for the aircraft, testing its stall characteristics, its roll rate, and its general handling. He found it to be a stable gun platform, but confirmed that it was sluggish in a low-speed turn. A Zero, he noted in his report, could easily fly circles around it if the Corsair pilot was foolish enough to engage in such a battle. This confirmed their existing beliefs and offered a small measure of comfort. If they could force the Corsair into a turning fight, they could still win. But that was not the primary purpose of these tests. The critical test was scheduled for a clear, crisp morning. Genda in the Corsair was to fly alongside two of Japan's top fighters, a brand new Mitsubishi J2M Raiden, or Jack, a fighter specifically designed as a high-altitude interceptor, and the formidable Kawasaki Ki-84 Hayate, or Frank, an Army fighter considered by many to be Japan's best all-around fighter of the war. Both of these aircraft were designed with the lessons of the new air war in mind. They had more powerful engines than the Zero, better high-altitude performance, and heavier armament. They were the best that Japanese industry could produce, the designated Corsair killers. The three aircraft took off and formed up at 5,000 feet. On a signal from the ground controller, the test began. The objective was simple: a maximum performance climb from 5,000 feet to 30,000 feet. It was a pure test of power-to-weight ratio and high-altitude engine performance. The race to the heavens had begun. Initially, for the first few thousand feet, the three aircraft were relatively evenly matched. The lighter Japanese fighters, particularly the Frank, even seemed to have a slight edge in acceleration. Genda held the Corsair in a steady, nose-high attitude, the double Wasp engine thrumming with a deep, resonant power. He watched the altimeter needle wind steadily upwards. 10,000 feet, 15,000 feet. It was here that the difference began to show. Genda engaged the supercharger's high-speed gear. He felt a surge of renewed power as the engine began to breathe the denser, compressed air. Outside his canopy, he could see the Frank and the Raiden beginning to fall behind. It was not a dramatic separation at first, just a slow, inexorable widening of the gap. Their engines, now operating in the thinner air where they were less efficient, could no longer maintain the same rate of climb. The Corsair, however, felt as if it were still climbing through the thick air of sea level, 20,000 feet. The Japanese fighters were now visibly below him and falling away more rapidly. Genda could imagine their pilots, their throttles pushed to the firewall, their engines straining at the limits of their performance, only to watch the dark blue American fighter pull effortlessly away from them. He felt a growing sense of disbelief. He was not just outclimbing them. He was leaving them behind as if they were tethered to the ground. 25,000 feet. He looked down. The Frank and the Raiden were now just specks, far below. He had not only won the race, he had demonstrated that it was not even a fair contest. The Corsair operated in a different performance category. He continued the climb, pushing the aircraft to its limits, the sky around him turning a deep, dark blue. 30,000 feet. He leveled off, the air thin and cold. He was alone in the upper atmosphere, the undisputed king of the vertical domain. On the ground, the engineers and military observers tracked the three aircraft on their plotting boards. The data confirmed what Genda was experiencing. The Corsair's rate of climb was nearly double that of the Japanese fighters above 20,000 feet. The performance charts they drew that day were a stark, undeniable illustration of the technological chasm. The verdict had been rendered, not in a laboratory, but in the unforgiving arena of the sky. When Genda landed, he was silent for a long time. He climbed out of the cockpit and walked over to the group of waiting officials. He was a pilot, not an engineer, and he described what he had experienced in a pilot's terms. "It is not a fighter as we know it," he said, his voice heavy with the weight of his discovery. "It is a climbing machine. It does not fight. It executes. You cannot catch it. You cannot follow it. If it has altitude above you, you cannot escape. The only way to fight this machine is to never let it get above you in the first place." His words were more powerful than any technical report. The test had confirmed their worst fears in the most dramatic way possible. The Corsair's ability to climb was not just a performance statistic. It was a tactical weapon of immense power. It allowed its pilot to control the vertical dimension, and in doing so, to control the entire engagement. The impossible climb was a demonstration of a power they could not match. Block 9. Echoes in Design, a race against time. The results of the Corsair's test flights sent a shockwave through the Japanese naval and Army aviation design bureaus. The stark, undeniable data from the impossible climb and the detailed engineering reports from Hiroshi Akiyama's team served as a brutal wake-up call. The era of the lightweight, agile dogfighter, as the supreme arbiter of the skies, was over. A new paradigm of speed, altitude, and overwhelming power had arrived, and they were dangerously far behind. The captured Corsair became a benchmark, a gold standard, against which all new and existing Japanese fighter designs were now measured. Engineers from Nakajima, Kawasaki, and Mitsubishi made pilgrimages to the naval arsenal to study the American aircraft. They pored over Akiyama's reports, memorizing the details of the supercharger, the metallurgy, and the rugged structural design. The Corsair's existence lent a new and desperate urgency to their own advanced fighter programs. The development of aircraft like the Kawasaki Ki-84 Hayate, Frank, and the Mitsubishi J2M Raiden, Jack, was accelerated. These were aircraft that had already been on the drawing board, conceived as answers to the growing threat of new Allied fighters. But now, with the Corsair as a known quantity, their design priorities were sharpened. For the Raiden, a point defense interceptor designed to protect the home islands from high-altitude bombers, the Corsair's climbing ability was a particularly terrifying benchmark. The Raiden's design was focused on a fast rate of climb and powerful cannon armament. Its designers worked feverishly to wring every last bit of performance from its Mitsubishi Kasei engine, trying to close the gap with the R2800. The Hayate, or Frank, was intended as a more versatile, all-around fighter, a successor to the nimble Ki-43 Oscar. After the Corsair analysis, greater emphasis was placed on improving the reliability and high-altitude performance of its Nakajima Homar engine. The Homar was Japan's own attempt at a 2,000-horsepower class engine, but as Akiyama had noted, it was a troubled design. The lessons learned from the Double Wasp's robust construction and superior cooling were applied, as much as possible, to the Homar program. Engineers tried to improve manufacturing quality control to solve the persistent oil leaks and vibrational problems that plagued the engine. The Frank that emerged from this period was a truly superb aircraft, arguably one of the best fighters of the entire war. In the hands of an experienced pilot, it could meet a Corsair on more or less equal terms, possessing a rare combination of speed, firepower, and agility. However, the echoes of the Corsair's technological superiority resonated in the Frank's persistent struggles. The Homar engine, while powerful when it worked correctly, never achieved the day-in, day-out reliability of the Double Wasp. Production was hampered by shortages of high-quality raw materials and the declining pool of skilled labor in Japan's besieged war economy. For every 100 reliable Double Wasps that Pratt & Whitney produced, Nakajima might produce only a handful of truly flawless Homar engines. This technological gap forced a significant shift in Japanese tactical doctrine as well. Pilots were now explicitly trained to avoid high-altitude engagements with Corsairs and Hellcats whenever possible. They were instructed to use cloud cover and surprise to their advantage, to try and lure the American fighters down to lower altitudes, where the agility of their own aircraft could still be a decisive factor. The classic, swirling dogfight was discouraged in favor of coordinated hit-and-run attacks. This was a profound change for a culture that had revered the individual skill and samurai-like honor of the one-on-one aerial duel. The Corsair, and the philosophy it represented, was forcing them to fight a different kind of war, one that was less about individual prowess and more about managing energy and avoiding the enemy's strengths. Beyond specific aircraft designs, the captured Corsair had a more fundamental, almost psychological impact on the Japanese engineers. It was a physical manifestation of the industrial might of the United States. It showed them that their opponent could build aircraft that were not only powerful, but also incredibly rugged and capable of being mass-produced by the tens of thousands. They saw in the Corsair a machine that was built to win a war of attrition, a war that Japan, with its limited resources, could not hope to win. This realization spurred a desperate race to develop what they called Kessenheiki, or decisive weapons. They began to experiment with more radical technologies. Rocket-powered interceptors like the Mitsubishi J-8M Shusui and jet-powered aircraft like the Nakajima Kika. These were bold, innovative designs, but they were too little, too late. They were the products of a nation that was no longer trying to compete on the same technological level, but was instead searching for a shortcut, a miracle weapon that could change the tide of the war. The irony was that even as they pursued these advanced concepts, they were still struggling to replicate the fundamental technology that the Corsair had demonstrated. The challenge was not just about building a jet engine. It was about building the industrial base that could produce the high-temperature alloys, the precision bearings, and the complex fuel systems required to make that engine work reliably. The echoes of the Corsair were a constant reminder of this deeper, more fundamental gap. The single captured aircraft on the ground in Japan had a greater impact on their design and strategy than 100 aircraft lost in combat. It was a silent teacher, and the lessons it taught were harsh, humbling, and ultimately impossible for them to overcome in the time they had left. It showed them the future of air power, a future that had arrived before they were ready. Block 10. Legacy of the Bent-Wing Bird, a lesson in ingenuity. The story of the captured Corsair and the revelations it provided to Japanese engineers is more than just a fascinating chapter in the history of military technology. It is a profound story about human ingenuity, the clash of different philosophies, and the immense impact that a single, well-designed machine can have on the course of history. The F-4U Corsair went on to build a legendary combat record, not only in the Second World War, but also in the skies over Korea. It proved to be an incredibly versatile platform, excelling not only as a fighter, but also as a formidable ground attack aircraft, its powerful engine capable of hauling a heavy load of bombs and rockets. The whistling death became a sound of comfort and relief to the Marines on the ground, a promise that help was on its way from above. Its legacy is etched in the annals of aviation history, a testament to the vision of its designers and the courage of the pilots who flew it. For the Japanese engineers who studied it, the Corsair was a turning point. It shattered their belief in the supremacy of their own design philosophy and exposed the limitations of their industrial base with stark clarity. The encounter with the double Wasp engine, in particular, was a moment of humbling revelation. It demonstrated that the war in the air was not just a contest of pilot skill or aerodynamic finesse, but a battle of thermodynamics, metallurgy, and industrial production. The efforts they made to catch up embodied in excellent late-war aircraft like the Ki-84 Frank and the J-2M Raiden, were a testament to their own brilliance and dedication. They were superb engineers who accomplished incredible things with limited resources. But they were caught in a race against an opponent who had not only started earlier, but was running on a fundamentally different track, powered by an industrial engine of unmatched capacity. This story, however, should not be viewed simply as a tale of one side's triumph and another's failure. It is, at its core, a human story. It is about the engineers at Vought and Pratt & Whitney, working long hours in Connecticut, fueled by coffee and patriotism, trying to solve complex physics problems to give their pilots an edge. It is about the young men and women on the assembly lines in factories across America, meticulously putting together the thousands of components that made up each Corsair. Their work, a vital contribution to a global struggle. And it is also about their counterparts in Japan, brilliant men like Hiroshi Akiyama and Kenji Tanaka, who approached their task with equal dedication and intellectual rigor. They were driven by a love for their country and a deep respect for the art and science of aviation. Their awe at the sight of the double wasp engine was not the sentiment of a defeated enemy, but the professional admiration of one group of masters for the work of another. It was a moment of pure, unadulterated engineering truth, transcending the conflict that surrounded it. The legacy of the Corsair, therefore, is twofold. On one hand, it is a symbol of a particular approach to problem-solving, the application of overwhelming power and technological superiority. It represents a philosophy where the best way to win a fight is to arrive with a machine so powerful that it can dictate the terms of the engagement, minimizing risk and maximizing effectiveness. On the other hand, the story of its capture and analysis serves as a powerful reminder of the importance of intellectual humility and the universal language of science and engineering. In that hangar in Yokosuka, the conflict was stripped away for a moment, leaving only a group of dedicated professionals studying a complex problem. They sought to understand, to learn, and to better their own craft, a drive that is common to all innovators, regardless of the flag they serve under. When we look back at the Corsair today, with its iconic bent wings and its massive nose, we see more than just a vintage warplane. We see a pivotal moment in aviation history, the point where the piston engine reached its zenith, a roaring crescendo of power and performance before the dawn of the jet age. We see a testament to the idea that sometimes the most elegant solution to a complex problem is a simple, brute force application of power. And we see a story that, in its essence, celebrates the human spirit of inquiry and innovation. It reminds us that even in the midst of the most profound conflicts, it is our ability to create, to analyze, and to understand that truly defines us. The bent-wing bird taught a powerful lesson to all who encountered it, a lesson written in the language of horsepower and altitude, a lesson about the relentless and awe-inspiring march of technology.